investigate how we can learn self-driving end-to-end, and in particular, how we can fuse the multimodal input data best, and how useful are attention mechanisms in this process. This is joint work with my amazing collaborators, Aditya Prakash and Kashyap Chita. The first walk I'm covering is Transfuser, multimodal fusion transformer for end-to-end autonomous driving that has appeared at CVPR this year. Let's have a look at this traffic situation. Traffic situations are complex. In this particular case, the ego vehicle has to attend to multiple faraway objects in the scene. And these objects each influence each other. For example, the state of the traffic light has an influence on the oncoming traffic on the left-hand side. And in order to make a robust decision, the ego vehicle has to anticipate this relationship. However, not all sensors can see all parts of the scene equally well. Typically,
Andreas, could you please increase the volume a bit?
Vehicles are equipped with RGB cameras and LiDAR sensors. RGB cameras deliver a dense RGB input image, but they lack reliable 3D information, and they are also varying with the weather. If the weather changes,
is this better?
The pixels can change dramatically.
Yes.
On the other hand, LiDAR point clouds directly provide 3D information. However, they are quite sparse, and they do not provide some of the relevant information in the scene, such as, for example, the traffic light state. Therefore, the natural question to ask is, how can we most effectively combine these two signals into a robust driving command? And this is the research question for this paper: how to integrate representations from multiple modalities. To what extent should the different modalities be processed independently? And what kind of fusion mechanism to use for maximal performance? One way of combining different modalities, particularly in this case modalities in 3D space like the LiDAR point cloud and the image modality, is to use a geometric feature projection. In this case, we're taking 3D points from the LiDAR scanner, computing features in 3D space from the point cloud, for example using a PointNet-like architecture. And then we're projecting those features directly onto the corresponding pixel location based on the calibrated sensor information. This is what we call geometric fusion, and it's a popular approach to fusing this multimodal data in 3D and 2D space. However, the question is if this is the best we can do. And in fact, we observed in our experiments on the Kala simulator that geometric fusion indeed underperforms in complex urban scenarios. Let me show you two examples. Here's a complex environment from the Kala simulator, and you can see that the vehicle collides. Here's another example where you can observe a collision with a cyclist. The problem with geometric fusion is that it lacks global context. For example, in this particular scene here, where we have the image on the left and the corresponding LiDAR on the right, for this yellow region here, which corresponds to the traffic lights, geometric fusion aggregates features from the blue region from the LiDAR. However, this region is rather uninformative. And instead, for safe navigation, it's actually essential to aggregate features from this red region, from the opposite side, the oncoming traffic. The oncoming traffic is not visible in the image, but it's visible in the LiDAR because it has a wider field of view. However, the information that's aggregated in terms of features with respect to these traffic lights is this region here in blue. Therefore, the key idea in our transfuser model is to use attention-based feature fusion to capture the global context of the scene across different modalities. Let's have a look at our transfuser architecture. The input is a single RGB image and a single LiDAR scan. Both of them are, well, the LiDAR scan is first mapped into a bird's eye view representation for easy processing with 2D convolutional networks. And then both of them are processed with a ResNet34 backbone, as illustrated here, that comprises or interleaves convolution and pooling operations. And in the end, pools features and flattens them to a feature vector that can then be combined with a pooling operation. Now the transfuser model at each stage of this spatial pyramid interleaves the features from the RGB image and the LiDAR scanner by integrating a transformer module. As you can see here, we have multiple transformer modules, one at each of these resolution layers of the network. And one of these transformer blocks takes features from both modalities, aggregates them, and then splats this information back into the original ResNet34 or ResNet80 streams for the individual modalities. So we do this multiple times until we hopefully have integrated more global context before reaching a decision at the end of the network. Let's have a closer look at such a transformer module. The key idea of the transformer module is to consider the feature maps, the image feature maps here, as a set of tokens such that we can apply a standard self-attention module from the transformer architecture. In this particular example, we have a 2x2 feature map resolution. In practice, we use feature map resolutions of 8x8 pixels. And what we do is we tokenize them by considering each of the cells in the feature map as one token. And then we simply tokenize the feature maps from the image stream and the feature maps from the LiDAR here at the bottom, as illustrated here. And we combine all of these tokens and pass them into a standard transformer module that then, as an output, produces another set of tokens, another set of features with the same number of tokens, which we can then split back to the individual streams. In summary, we consider feature maps as sets of tokens where the cells of grids correspond to the individual tokens, and we pass all tokens to a self-attention mechanism, the same as used in the transformer module for natural language processing, which we then reshape back, the output of which we then reshape back into grid form. Having reached the output here, we aggregate the information via pooling, via summation, and then pass that into a GRU-based autoregressive waypoint prediction network, which is in addition conditioned on the goal location, as illustrated here. Therefore, our model doesn't produce directly the low-level control command, but it produces a set of waypoints which we supervise using an appropriate loss function, and these waypoints at test time are then input to a simple PID controller. This paradigm of predicting waypoints instead of directly the low-level control has demonstrated better performance in prior works, and that's why we follow this line of research here. As experiments, we consider a data set from the Kala simulator with 8 towns and multiple weather conditions. And we consider routes of varying length in complex urban scenarios. The export policy is based on an A-star planner and various collision avoidance heuristics. As sensors, we use one RGB camera with a resolution of 400 times 300 pixels and a 100-degree field of view, and a LiDAR with an 80 meters range, 64 channels, and 10 Hz rotation frequency. Here are some results on our internal evaluation. We used Town 5, which is one of the hardest towns in the Kala training town set. And so we train on all the other towns and test on Town 5, where we use both short and long routes for testing. And what we see here is the driving score and the route completion score. Higher is better, where the driving score is the primary metric for evaluation in the Kala simulator, as it integrates both route completion as well as infractions. And what we plot here is the mean and the standard deviation over 9 runs, where we use 3 different training seats and then 3 rollouts per seat for evaluating the models. The first 3 models here only use a single modality. They use only images as input. SILRS was the state-of-the-art model in Kala in 2019, and learning by cheating was the state-of-the-art model in 2020. We can see that through fusion, we obtain a significant gain in performance, in particular in the driving score. And we also observe that our baselines, we have one baseline where we do the fusion late without the transducer architecture. We are just processing the inputs independently using the ResNet backbones and then do the fusion. And we have another geometric fusion baseline. Both of them perform less well on these challenging Town 5 scenarios, in particular when we consider longer routes to be completed. What we also can observe is that the proposed transducer architecture drives a little bit more cautiously. It isn't able to complete as many routes as some of the baselines can do, but it achieves a significant larger or fewer infractions, which leads to a higher driving score. This is analyzed here, where we plot the different infractions based on infraction type on the x-axis. For example, collision with pedestrians or with vehicles or with layout elements, or red light violation. And you can see the transducer here in green provides the lowest amount of infractions. In other words, the safest driving behavior amongst all of these methods. Let's now look at the Kala leaderboard, and this is a snapshot of the Kala leaderboard at the time of submission of the paper. By now, of course, the scores have increased. We can see that again, the same behavior occurs. The driving score of the models that integrate LiDAR and images perform better than the models that use just the image as input. And also, the driving score of the transducer architecture is better than the late fusion or the geometric fusion baselines. On the Kala leaderboard, which evaluates on a held out city, and can be considered as a test of out-of-distribution generalization, we observe that in this case also the route completion score is higher compared to the baselines, which means that the transducer architecture also helps in generalization. Let's have a look at a video of the results. On the left, we can see the geometric fusion baseline, and on the right, the proposed transducer architecture. While the baseline collides with vehicles due to its inability to reason about complex global context, the transducer architecture yields to much safer driving behavior. Here are some examples where we demonstrate generalization to novel weather conditions. These are weather conditions that haven't been observed during training time. And because weather heavily influences the image modality, this generalization type often poses challenges to end-to-end self-driving agents. Yet we also observe the same behavior. Transducer takes advantage of contextual reasoning and therefore provides safer driving behavior. In order to better understand what the attention mechanism does, we visualize the attention maps here. What we can see here are the tokens. For example, we consider a query token in the image domain on a traffic light in orange. And then we look at which are the top 5 tokens in the other modality here, in this case the LiDAR, which is illustrated here in green. And we can observe that indeed the model has learned that this traffic light is causally related to the other vehicles, the oncoming traffic from the left. So it attends to this region here, and the red region indicates one particular vehicle that's on the road. This has been manually labeled, just to illustrate that the region that is attended to actually makes sense. Here's another example where we use a query token in the LiDAR modality here in orange, which is on a vehicle. And we observe that in the image where this vehicle is not visible, the model attends to the traffic light on the other side of the road and other vehicles in the scene. And here's another example where now we have the oncoming traffic directly in front of us, where for a particular token in the LiDAR modality, the model actually attends to the same vehicles in the image domain. This was the first part of the talk. In the second part, I'm going to be talking about a recent work that we are presenting at ICCV 2021 called NEAT, Neural Attention Fields for End-to-End Autonomous Driving. And in this work, we aim at developing a image-based only self-driving agent. And we're wondering what is the right representation to use? What is the right intermediate representation, and how can we incorporate attention mechanisms here? And we argue that the bird's eye view is an ideal representation. Why is that? Well, first of all, it's crucial that we can efficiently reason about the semantic structure and the spatial and temporal structure of the scene for self-driving. That's pretty clear. Here are some examples of complex driving situations. You can see that all of them exhibit complex semantics and spatial and temporal structures. But driving doesn't happen in image space. Despite, in this case, we're only provided with 3 cameras as input, driving happens in the physical 3D world. So we should also perform our reasoning in physical 3D space. And the bird's eye view, as illustrated by the semantic maps corresponding to these different scenes here on the right, is an effective approximation for 3D space. Because typically in self-driving, there's not so much that happens in the third dimension, in the upwards dimension. So if you have a good sense of the scene from bird's eye perspective, then driving can be conducted in most situations safely. Now the question, of course, is how to obtain a compact and interpretable bird's eye view representation from images as input. Bird's eye view semantics for driving is not new, and there have been a couple of works that have explored this direction. For example, in learning by cheating that we have already talked about, a teacher model is trained on privileged information that's provided in terms of bird's eye view semantics to the teacher model. And then a student model that only has access to images is trained against that teacher model in order to exploit the pre-trained teacher model. And Roach is a more recent approach that also makes use of the idea of training an expert, improving an expert using privileged information and training then a student against that expert. What we do in contrast here on the right in our approach called NEAT is multitask learning. We have, instead of 2 training stages, we just have a single training stage where we use bird's eye view semantics, which is not directly needed for driving, but we use this as an auxiliary task. And this allows us in a single training stage to train our model. And furthermore, we integrate selective attention mechanisms that bridge the gap between the perspective to the image space and the bird's eye view space, the physical 3D world space. The representation that we're using is an implicit one. It's an implicit one that implicitly and recurrently queries the input images. Here's an example for an implicit representation that represents semantics. The input to an MLP is the x, y, t location, which is the spatial and the time dimension here. So for this particular location in space-time, we want to query the semantic class label. This has been explored recently for other tasks like 3D reconstruction, motion estimation, and appearance prediction, but it hasn't been used heavily for robotics yet. So we are trying to now exploit this idea of implicit representations for self-driving. The advantage of such an implicit representation is that for any continuously represented input location, we can query now this network, and we can query any quantity, for example, semantics, but also waypoints. What we do for waypoint prediction is the output here is a so-called waypoint offset. So for example, at this location, the model outputs the offset to the actual waypoint for that particular location in space and time. Here on the x-axis are multiple time instances. So we can represent both semantics and waypoints implicitly. And we can do this at arbitrary spatial and temporal resolution and with a very small memory footprint because these MLPs are very compact. And then we use this representation in combination with an attention mechanism to iteratively query the input image. What we can also see here at the bottom in this particular illustration is that we can also represent in this bird's eye view representation the target, the goal location, which is provided by the high-level planner, the GPS planner. This is the desired target location. It's very coarse and sparse. It only happens every 50 meters or so. We get an observation here. We call this x prime and y prime. But because we are now doing reasoning in this bird's eye view space, we can incorporate this. We can add this as an input to the MLP, which we do in practice. Similar to the x, y, and t coordinates that we input to the MLP. So we can incorporate in a very flexible way, varying conditional information. I was muted. Okay, sorry. So I'm saying that again. So I'm gonna jump ahead a little bit now because in the interest of time, I'm gonna go over the like the exact model definition. But what I want to say here just quickly is that we have an implicit representation that's iteratively queried through such an attention mechanism as well. So we have a transformer that produces tokens from the inputs and from the state variables, and then these are iteratively transformed, and then the implicit representation is responsible for producing the output. So I'm going to go forward now to the video. You can see the waypoint predictions here on the top right. These are the waypoint offsets, and then the final waypoint that is regressed is this red dot. The blue points are the target location that are provided by the high-level GPS planner as input to all of the agents that drive. Of course, it's necessary to have this information because otherwise we wouldn't be able to know at intersections where to head, in which direction to turn. At the bottom, you can see the bird's eye view semantics that's predicted as an auxiliary output of our system. And by predicting both, we obtain the highest driving score with our system. Okay, let me stop that here. So, yeah, I want to thank you for your attention. Here are some conclusions. In this talk, shown that the global contextual reasoning is crucial in complex urban scenarios, and that attention is effective in aggregating, or can be effective in aggregating information from multiple modalities. And this allows for navigation of challenging intersection scenarios. And also shown that joint bird's eye view semantic prediction and trajectory planning can lead to safer driving, and that an implicit intermediate representation can solve this task quite efficiently. Thank you very much, and looking forward to any questions that you might have.